So welcome you back. So let us try to revisit what we were doing during the last lecture. So we started with invariant estimation, and the need for invariant estimation arose because what we realize is if we consider the class of all estimators into consideration, then finding the best estimator is not possible because this class is too big. So it is not possible to find an estimator which minimizes the risk for every parametric point. So what we do? So to get rid of this problem, we say that, okay, let us try to put some reasonable conditions on the kind of estimators we would be considering. So for example, one reasonable condition was unbiasedness, which you did in the last course. And once you put the unbiasedness condition, your class of estimators is reduced, and then you can find the estimator which minimizes the risk for every theta in terms of a squared error loss function. That turns out to be the uniformly minimum variance unbiased estimator, and we saw that in many situations uniformly minimum variance unbiased estimator exists. Now, invariance is another reasonable restriction which you may like to put on the class of estimators under consideration. So we did it last time, but let us try to revisit it once again. So let us consider the model which we are dealing with. So suppose you have a data x1, x2, xn. This has a distribution function f which belongs to the family P. Now this family P could be parametric, it could be non-parametric. So to make the thing simpler, let us try to restrict ourselves to parametric case, and which is what mostly we will be doing in this course. So suppose this is f theta, theta belongs to capital theta. So in the parametric setup, you know that functional form of f theta is known. What is unknown to you is theta. So the only unknown quantity is theta. Goal is to estimate some function of theta. So let us say g of theta. I have been using consistently the notation g of theta for estimate. Now g I will be using for some group of transformations, so let me introduce alternate notation over here. So suppose I am interested in estimating psi theta based on the sample or the data I have. Now as I said, because your sample contains only partial information about the population, so whatever decision you take, it may be erroneous. So there may be some error in the decision which you take. So this error is measured in terms of a loss function. So I say that L theta A is the loss in estimating psi theta by A when theta is true parametric value we also say that when theta is the true state of nature. So I have a loss function. Normally you assume that your loss function is non-negative. It is convex in A, and we know that if it is convex in A, then you can consider only the non-randomized estimators. So L theta is some loss function which is given to you. Now this xn, whatever xn you take, it has to, because your xn is based on x, you take an xn. That look, this is an estimate of psi theta. So my xn space should be nothing but collection of all possible values of psi theta such that theta belongs to theta. So whatever xn you take is one of the possible values of psi theta. So this is called xn space. Then you gave a definition of a decision rule. What should be a decision rule? Because based on x, you have to take a certain decision, or you have to choose certain action. So I gave a definition of a decision rule, which we called as non-randomized decision rule or non-randomized estimator. So to consider the estimators in the most generality, we said we can consider an estimator to be a probability measure on the action space A. So this is delta is a map from chi cross A to 0, 1, where this chi is nothing but my sample space, which is the space of possible values of the data, which would be a subset of n-dimensional Euclidean space here. And what is the interpretation of this? For every x in the sample space, so every time I observe x, delta gives me what is the probability of choosing various actions. So delta dot x is a probability measure on action space A. Now every probability measure I can associate a random variable corresponding to it. So I say that this is a probability measure of some random variable yx. Note that for every x I get a different probability measure, because every time you observe x, it tells you how to choose various actions. And then the typical kind of estimators which you studied in your last course were the non-randomized estimators. Now, non-randomized estimators correspond to a situation where this probability measure is a probability measure of a degenerate random variable. This is a definition of a randomized estimator. I messed it up a little bit. So this is a randomized estimator. So what is a non-randomized estimator? Non-randomized estimator is a particular case of randomized estimator where delta is a probability measure, of a degenerate random variable yx. So you can write down this is a probability measure for every x. So delta dot x is a probability measure of a degenerate random variable yx. So what does that mean? That is, for every x belonging to sample space, yx takes only one value with probability 1. So probability that, so for every x belonging to ax, there exists ax such that yx takes the value ax with probability 1, such that probability that yx is equal to ax is 1, which is equivalent to saying that if I have to write down this everything in terms of delta dot x, so this delta a given x is nothing but probability that yx belongs to a, because it is a probability measure of random variable yx, so it is a probability yx belonging to a, and I know that yx takes only value 1, which is ax with probability 1, so it would depend whether ax is in this a or not. If ax is in a, this probability is 1. If it is not in a, then the probability is 0. 1 if ax belongs to a, 0 otherwise. So what does non-randomized estimator does? For every x, it chooses only one action with probability 1. So that means there is no further randomization is required after you have observed the data. In the randomized estimator, because you are considering a probability measure, what it says is for every x, your action should be a random variable yx, and yx you observe through conducting another random experiment. So as I said, gave an example that one example of randomized estimator could be, suppose sample is of size 1 and x is normal theta 1. I say you observe x, and after observing x, I go to my computer and I generate one sample of size 1 from normal with whatever observation I have, let us say x, comma 1, and I take that as an estimator. So there is a two-stage procedure. First stage, there is a randomization over there, So after observing x, I do a randomization, and then I choose my estimate. Non-randomized estimator, after observing x, you immediately take an action. No randomization is necessary because this y-x is degenerate at ax. And for this reason, non-randomized estimator can be simply written as delta of x. Because after x, after you observe x, it gives me an action. So delta x is an action. So without loss of generality, I can denote a non-randomized estimator by delta of x. So let's look at what is the goal of invariance. Goal of invariance is that, look, principle of rational invariance and principle of invariance says that if two estimation problems have the same formal structure. So let's look at what do we mean by a formal structure of an estimation problem. So what are the components of an estimation problem? A random vector x, which has a distribution f theta, where theta is in capital theta. Corresponding to that, I have an action space A, and then I have P or P, yeah, which is class of all distributions. So this is a typical estimation problem. There is no, this P is covered through theta, so theta A and loss function L. So an estimation problem is characterized by this triplet theta A L. So the principle of rational invariance says that my final decision should not depend on the units of measurement or any other such quantity. See, whether I am measuring height in inches or centimeter, as long as my formal structure of the estimation problem does not change by converting centimeter into inches, the final decision should not matter. It should be the same. That means the decision of centimeters should be converted into inches, and the two should correspond. Not only that, it also says that if two estimation problems have a same formal structure, then I should use the same decision rule. For example, if I say that my height of students at IIT Kanpur is normally distributed with mean theta and variance 1, and theta is unknown to us. I also have, suppose, assumption that height of students at Bombay also has normal distribution with mean theta and variance 1. So the means may be different, but what I know is the height is normally distributed. So height of students is normally distributed. So he says, I am dealing with two estimation problems. He says, if you are using a sample mean to estimate the sample mean of heights at IIT Kanpur to estimate the mean of height, mean height of students at IIT Kanpur, you should use the same sample mean. Of course, now the sample mean will be the sample mean of the sample taken from the IIT Bombay. So sample mean should be used at both the situations. The value of the sample means, of course, will be different. So the same decision rule, same estimator, I am using the sample mean at both the places, because the two had the same formal structure. So let us try to explain this in terms of a transformation which we discussed last time. We defined what do you mean by a group of transformations. So let us try to see that in this context, in the context of invariance. So suppose you have a x has a distribution function f, right? Now what you have is, and this f suppose belongs to P. Now there is another situation, so this could be height in centimeters. I am now measuring height in inches. Height in inches is, that means you apply certain transformation to x. So now I have a y, a new observation y, which is g of x, so which is equivalent to saying that if x was in centimeters, I have applied I have converted it into inches, which is equivalent to saying that I have applied certain transformation on it. And suppose y of gx has a distribution function g bar f. So that means if x has a distribution function f, y is equal to gx has a distribution g bar f, which also belongs to P. So that means my transformation G says that my distribution is in the same family. So like as it happens when you're talking about normal theta 1, if x is normal theta 1, x plus c is also normal theta plus c and 1. And if theta is in R, theta plus c is in R. So my P remains the same. Because if theta was in R, so theta plus c is also in R. And P was nothing but all normal theta 1 says that theta belongs to R. So suppose you have a situation like this. Here you may be interested in estimating psi of theta, let us say. So let me write down this as f theta, because I'm dealing with a parametric setup. So y is equal to gx has distribution function. Again, f of some theta, so that theta suppose gets converted to f of g bar theta, which also belongs to P. So I'm interested in estimating psi theta over here. So certainly I'll be interested in estimating psi of g bar theta over here. Right? Otherwise, the set of distributions is the same. Now, what I assume is if my the losses are also same. So here, loss in estimating theta A, loss in estimating psi theta by A should be same as the loss in estimating g bar theta by some another xn. So that means what I assume is there exists a star belonging to A such that L theta A is same as L of g bar theta and A star. So for every A belonging to A, there exists an A star over here such that L of g bar theta. So that means the two losses are the same, except that here you are estimating psi of theta, here you are estimating psi of g bar theta. So I assume that in the two situations, the loss in estimating psi theta by A should be same as loss in estimating g bar theta by some other xn, which I am calling as A star. Now this A star normally I denote it by T tilde. So what I assume is there is a transformation so that my class of when I apply that transformation to x, I remain in the same family P. And then my loss function is such that for any g bar, I can have an xn equivalent xn over here such that the losses in the two decision problems are same. So this is a situation where the formal structure of the two decision problems is same, except that in one of the estimation problems you are talking about change of units through the transformation y is equal to gx. So what does this say? Principle of invariance is, so suppose I use here a decision rule delta and I use a decision rule delta star over here. So what is the decision rule delta over here? It will tell me what is the probability of taking xn A when x is the observed value. This will tell me what is the probability of taking xn in this xn space over here when gx is the observed value. So it says that delta should be same as delta star because the two problems have the same formal structure. Because my P remains the same, my xn space will remain the same, and my loss are the same in the two situations. So it says I should use the same decision rule. So this is principle of invariance. Not only that, it says that two xn's would correspond. So what does that say? The xn over here is yx. What is the xn over here? Y when gx is observed. So what is happening over here? The xn should correspond to over here means what is the corresponding xn over here? If a is an xn over here, the corresponding xn over here is g tilde a. So that means if yx is an xn over here, the corresponding xn over here is g tilde a. So that means g tilde of yx should be same as y of gx. Right? That is what is happening. If you look at, I am saying there is a correspondence of xn in the two TCN problems. If a is an xn over here, which was for estimating psi theta, the corresponding xn here is g tilde a, which is for estimating psi of g bar theta based on x, based on gx. So this is what it means. So what it is equivalent to saying that delta of a given x is same as probability that y of x belongs to a for this decision problem. This should be same as probability that g tilde or yx is nothing but g tilde inverse yx belongs to a, which is same as what I have done. No, yx belongs to a, yx is nothing but g tilde inverse y of gx belonging to a, which is same as probability that y of gx belongs to g tilde of a. But what is this? Yx was corresponding to probability that, what was the y of x? Y of x was an xn over here, which is y of x was nothing but delta of a given x. So probability that yx belongs to a is same as delta of a given x. So what is the probability of y of gx belongs to g tilde a? That is same as delta of g tilde a given g of x for any set a, for every. So it says my decision rule should satisfy this. Now this is nothing but a definition of a invariant decision rules. So the purpose of this discussion was to show that, look, my invariance principle demands that I should only consider estimators of this type. That means those which satisfies delta of a given x is same as delta of g tilde a given g of x. Or in other words, if I talk in terms of corresponding random variables, then g tilde y of x should have a same distribution as y of g of x. Now I can generalize this whole discussion to any set of transformation. This was just one single transformation. There is a possibility that such a thing holds for a group of transformations. And then I can extend all this, and I say that I should only consider all those decision rules which satisfy this as g varies over that group. So let's do that. So now I have given you a motivation. Now I'll try to build up the whole invariance theory step by step. So let's see what are the steps involved. First step involved is that transformation should be such that if I apply any transformation in that group, my distribution should be in the same family. So I would need a definition of the family P of distributions being invariant under a group of transformations. That is number one. Second thing, I wanted my laws to satisfy certain invariance property. So the second step involved would be to say that when a loss is invariant under the given group of transformations. Once that is happened, then I can say that my problem is invariant, problem of estimation is invariant. Now, if my problem of estimation is invariant, then I say that I should only restrict to invariant decision rules, which are reasonable decision rules, which gives me a definition of an invariant decision rules. And then I can talk about finding the best invariant decision rule or best invariant estimator. Because now I have restricted our estimators under consideration to be only invariant estimators. And then there is a possibility that we may be able to find the best estimator within this class. So let us do this one by one.